Hello, my name is Nitin. Finally, I have received the DAISY 8 module APD version 1.2 from SPIAG. I had to wait until the regulators in Japan and South Korea were fully equipped and operational. Today, I am going to conduct an initial review of the new module. These are the components I have received. First of all, the new APD version 2 probe developed by SPIAG. This probe is based on the same principle as the free space millimeter wave probe, but is encapsulated with a material that has dielectric properties similar to those of the skin simulating material. This design helps to reduce scattering. The significant advantage of this pseudo vector probe is its high sensitivity and accuracy, as distortions caused by the probe can be compensated in the calibration and measurement process. However, the main drawback is that it requires 3 measurements per location, increasing the measurement time. As we know, SPIAG is renowned for prioritizing precision over everything else. I also received the Data Acquisition Electronics DAE 8 APD with an improved surface detection mechanism. This is important as 0.2 millimeter uncertainty is insufficient at these high frequencies. Another component is the new PHA 30G APD Phantom. As the name indicates, the narrowband multi-layered phantom mimics the transmission and reflection in the frequency band from 24 to 30 GHz. The skin simulation liquid SSL30 has been designed together with the phantom. It is valid for the same frequency range from 24 to 30 GHz and has low loss. In other words, much larger penetration depth, but combined with the phantom, the same absorbed power density as skin. Finally, I have the phone mounting device MD4 APD version 5 to position the handheld transmitters precisely below the phantom. Now, I am setting up the system. After filling the phantom with 1 liter of SSL30 and verifying its properties with the DAT 1.2E coaxial probe kit, I add the vapor barrier balls. These balls prevent the degradation of liquid properties due to exposure to humidity. The setup is now ready for testing. For a first check, I mount the 30 GHz APD verification source in touch to the phantom bottom. It is a 30 GHz horn antenna fed with a gun oscillator, fully calibrated at SPIAG in Zurich. My objective is to compare my measurements with the target values from the calibration certificate. The measurement project consists of a 50 mm into 50 mm APD scan anchored to the device under test reference point. The recommended resolution for the scan is 0.5 lambda inside the liquid. I will now start the scan. The planar scan is preceded by a localized mother scan verification to enhance positioning accuracy. The APD scan is a planar scan measured at 1 mm from the phantom surface, with the probe tip being just 200 micrometers from the phantom surface. Towards the end of the scan, a vertical Z scan is used to measure the field decay at the peak location. The measured field and its decay are used to compute the APD values at the phantom surface. The measurements are now finished and we can quickly visualize the results. The 1 cm square and 4 cm square circular averaged APD value for this source works out to 66.8 and 39.9 watt per meter square. The deviation from the target values are 0.35 and 0.2 dB respectively. These are pretty good considering the high frequency and resulting field gradients involved in this measurement. The available field display quantities include the field magnitudes as well as the circular and square averaged power density. The APD module, hardware and software are specially optimized for maximum sensitivity and measurement in high field gradients. While the probe is broadband and can be used from 10 to 45 GHz after the necessary calibrations, the phantom and liquid combinations are band specific. SPEAG mentioned that new phantoms will be added to cover other bands in future releases. The software is easy to use and will require a very short learning curve for existing module SAR or millimeter wave users. The ability to reuse most of the existing DAISY 8 hardware brings a short return of investment for the lab. Thanks for watching this video.